There are two most popular methods to create artificial gravity. The first one is by using constant linear acceleration. You've probably felt this before when riding in a car. When the car accelerates, your body is pushed back into the seat. That happens because of inertia. In the same way, if a spacecraft were to accelerate constantly along one axis, the crew would feel an inertial force in the opposite direction, which could simulate gravity. It's also similar to the feeling you get in an elevator that's accelerating upward. Your body feels heavier, as if there's an extra force pulling you down. This approach seems elegant and simple, but in practice, it's highly inefficient and unrealistic. To maintain constant acceleration, a spacecraft would need an enormous amount of energy, far beyond the reach of our current technology. The second method is much more realistic, and it's often shown in science fiction movies like Interstellar. The idea is to spin a habitat or space station at a constant angular velocity. In this method, we don't rely on changing velocity to generate acceleration like Method 1. Instead, we generate acceleration by changing the direction of velocity. In rotational motion, the changing direction of velocity creates an inward acceleration called centripetal acceleration. Because of inertia, the astronaut inside feels as if they're being pushed outward. This fictitious force is called centrifugal force, and it's the one we use to simulate gravity. Also, from the energy perspective, this method makes a lot more sense. You only need to spend energy to start or to stop the rotation. Once started, the station will keep spinning in the vacuum of space. Mathematically, the artificial gravity acceleration can be calculated using this simple formula. Acceleration is equal to angular velocity squared times the distance between the point and the center of rotation. This means the faster the spin, or the larger the radius, the stronger the artificial gravity you can feel. Although the theory sounds straightforward, this method still comes with its own set of challenges. And these are key reasons why artificial gravity hasn't yet been implemented for astronauts. We'll dive into those issues in this video later. To see if the theory holds true, I set up an experiment using an electronic device to control a motor at precise angular velocities, along with an accelerometer to measure its acceleration. After testing it at different angular velocity, I collected the data and compared it to the theoretical predictions. As you can see in the chart, the experimental results matched the theory very closely, with errors between just 1 and 3%. This simple experiment demonstrates that the concept of artificial gravity is not just science fiction. It works in reality. The real question is, if the physics is so straightforward, why hasn't this concept been implemented in space yet? If we analyze it using the formula for artificial gravity acceleration, we realize that the artificial gravity felt by an astronaut is not the same at the head and the feet. This is because the distance of the head and feet from the center of rotation is also different. On a large rotating station, the difference in gravity from head to feet is small and generally not a problem. But on a smaller station, the difference becomes significant. For example, an astronaut who is 2 meters tall inside a habitat with a radius of 100 meters would feel only about a 2% difference in gravity between head and feet. In contrast, in a habitat with a 10-meter radius, that same astronaut would feel about a 20% difference, large enough to cause discomfort and health issues over time. Another issue is that in a rotating habitat, every point at a different distance from the center has a different tangential velocity. The farther from the center, the greater the velocity. As a result, the astronaut's body experiences a difference in tangential velocity from head to toe, which can increase discomfort and cause health issues like dizziness and motion sickness. This velocity difference also gives rise to the Coriolis effect, which makes moving objects seem to curve. For instance, when an astronaut pours water into a glass, the stream doesn't fall straight down, it curves. To reduce these effects, the radius of the habitat must be made very large. That way, the difference in gravity between the head and feet, as well as the Coriolis effect, becomes small enough to be negligible. But the trade-off is enormous. It would require an immense amount of material with incredible strength to withstand the massive centrifugal forces. That's why, even today, the concept of rotating space habitats is still considered extremely difficult to build with our current technology. But we will never know. Maybe in our lifetime we will witness the first artificial gravity start to be implemented in space.